This is section 12.6, and in this section we're going to look at the first coordinate change that we'll use for triple integrals, which is what we call cylindrical coordinates. We'll figure out how we can change a triple integral into cylindrical coordinates and then evaluate. So first let's just define what we mean by cylindrical coordinates. If I have a point here in XYZ space, then I'm going to define z in cylindrical coordinates to be the same z we've been working with all along in Cartesian. So this is the same Cartesian z. And then the Cartesian coordinate z. And then r and theta are going to be the polar coordinates of the projection of the point onto the xy plane. So it's pretty easy to transform back and forth between the two given what we learned already with polar. So if I want to do cylindrical to Cartesian, then just like in polar, x is r cosine theta, y is r sine theta, and then z is just the same z in both coordinate systems. And then similarly, I can go the other way, Cartesian to cylindrical, and it looks almost identical to what we had with polar, just now we're adding in this third coordinate. So let's talk about what types of regions would be useful for integrating in cylindrical coordinates. In general, they're useful for describing surfaces and curves that are symmetric about the z-axis. And let's take a minute and try, in this example, I want you to try to sketch what these regions look like, and they're just surfaces in this case, what these surfaces look like in 3D, given that I've described them in cylindrical coordinates. I want you to sketch them in Cartesian. So go ahead and put this on pause and see if you can sketch each of these. All right, so the first one is saying that r is equal to 2, and theta can be anything and z can be anything. So if I am just looking in the xy plane, that would just be this circle of radius 2. But now z can be anything. So it's actually going to be this entire cylinder of radius 2 that's centered at the origin and opening along the z-axis. Now for part B, I've specified two things. R needs to be 2 and theta needs to be pi over 4. So let's let this be pi over 4, and then we can say this total distance here, which is r, would be 2. And that needs to hold, so it's definitely, this point is on, or it satisfies both. But this is also true for any z, because I don't have any restrictions on z. So it's actually going to be this line that goes all the way in 3D. Okay, now let's look at 1c and 1d. So anytime you have an equation in cylindrical that relates just z and r and doesn't involve theta, where theta can be anything, there's two ways you can do this. So the first way is you can just convert directly to Cartesian. So we know z is z in both cylindrical and Cartesian, but then I'm going to convert r squared, and we know that that is x squared plus y squared. And then we could sketch this, because this is one of the quadric surfaces that we learned back in chapter 10. And so if you recall, this is the quadric surface. This is an elliptic. Well, actually, this one's a circular, but technically it's more general to call it an elliptic paraboloid. This is the bowl shape that's opening down, starting here at 1 and coming down like this. Okay, now if you hadn't seen that, the second option is you can sketch this, a cross section here, just in the ZR plane. Now let me really specify what I mean by the ZR plane. So here in Cartesian, let's say this is x, this is y, this is z. For a fixed theta, let's say I just fix my theta, I can sketch this ZR plane. Here's C, here's R for a fixed theta. And I know that this equation up here has to hold for any theta. So what I'm going to do is just sketch this for just one theta here in my ZR plane, and then I'm going to rotate this around. And in general, in Cartesian coordinates, or excuse me, in cylindrical coordinates, we are going to restrict R to always be positive so that we don't end up with more than one representation for the same point. If we restrict R to always be positive and we allow theta to go from 0 to 2 pi, then there's only one way we can describe each point in space. So that's what we're going to sketch. We're going to sketch it in the ZR plane, assuming R is positive. And we can look at this equation and realize that that's just going to be a parabola opening down in the ZR plane that's starting up here at 1. And so now I can go sketch that here in my 3D plot. So I'm going to try to kind of sketch it on its side. And then I realize it has to be that exact same curve for all theta. So now I imagine in my head rotating that ZR plane all the way around 360 degrees around the z-axis and sketching out what I would get. And so you can see as I would rotate, and even along the back there, I would end up with the same answer we got above, this paraboloid. So let me, just to make it super clear what I just did, let's highlight this one. So you can see how I just sketched a random one and then I rotated around. All right, and then just a reminder, we can do this because there's no theta in the equation. So this little trick only works when you just have z and as a function of r. Okay, we can do the same thing here in 1D. So let's actually skip to that option first. 1D, I can also just sketch the ZR plane. And so I'm just going to do it for positive r again. And we can see this is just going to be a line in my ZR plane. And so I'm now going to take that line and I'm going to translate it. Let's put a little ZR right here. And now I'm going to sketch this line. It's going to be a little bit hard to see the perspective, but I'm trying to draw like that. And then now we're going to rotate this around for all theta. And you can see this is going to trace out for us a top cone. And if we hadn't seen that trick, you could also have done this using option 1, which would just to be rewriting it in Cartesian. So using that, I'm converting r to Cartesian, which is just going to be positive square root of x squared plus y squared. And again, that's one of the forms of the quadric surface that we've graphed before. The full quadric surface we've had is the full cone. And so this is the full cone. And so this is just the top cone. All right, so either of these options are great for sketching. And now let's go to how we could integrate over regions that look like this. So, because any of these regions, a cylinder, this paraboloid, a cone, they're all going to be great options for switching to cylindrical coordinates if you're trying to integrate over a region like this.